Now we'll start the topic of rectilinear motion. Rectilinear motion can be directly written as motion of a body along a straight line. When a body moves along a straight line, either forward or backward, in either direction, when a body moves along a straight line, this motion we simply call as rectilinear motion. And in case of rectilinear motion, as body moves only along one dimension of a coordinate system, we can simply write it motion in one dimension. So motion along a straight line can be either termed as rectilinear motion or motion in one dimension. Before proceeding further in motion in one dimension or motion in 1D, we must understand one thing very carefully, that is reference frame. The concept of reference frame itself is very important to understand. Almost in all problems of mechanics, which we'll study further, reference frame is simply, you can simply say it is a region or a zone from where observations are taken for motion parameters of a body. When we talk about observations for motion parameters of a body, when a body moves, with the motion of a body, the parameters which are associated are simply, we can say, displacement, velocity, acceleration, time, parameters associated with the motion of a body. The region from where all these observations are taken, we define as a reference frame. Reference frame, it can be at rest or maybe in motion, maybe moving. Like for example, if you are standing on ground, say for example you are standing on ground and you are looking onto a body which is moving at a speed of 10 meters per second, then in your reference frame or with respect to ground, we can say the body is moving at 10 meters per second. But the same body, when observed by a boy who is say standing on a skateboard which is moving at some other velocity, say 10 meters per second, then we can say this boy who is moving at a speed 10 meters per second, he'll feel that this body X is at rest, because both of these are moving at a speed 10 meters per second. So we can say this boy will not observe any motion in this body. So in the reference frame of observer A, this body is moving at 10 meters per second, and in the reference frame of observer B, this body is at rest. So reference frame we can simply define as a region or zone from where observations are taken for motion parameters of a body, and either of these parameters can be recorded when a moving body is observed from a given reference frame. If we take up another example to understand the concept of reference frame, say we are having a car which is moving at a speed of 3 meters per second and a boy who is standing at rest on ground. So we can say the reference frame of this observer is ground. Here we can say reference frame is ground, because he is measuring the motion parameters of this car from ground. Now if we consider another observer who is moving on a trolley like this, say this is observer A and this is observer B, who is on a trolley which is moving at a speed of 1 meters per second. So here we can simply call reference frame as trolley. Now from this trolley, this observer B is measuring the motion of car. So here we can say the speed of car with respect to ground frame is, simply we can call velocity of car as measured from ground frame as 3 meters per second. And here if we measure speed of car with respect to reference frame of trolley, in this equation velocity of car as measured by the observer B can be written as car is moving at 3 meters per second, and this trolley is moving at 1 meters per second. In 1 second it will travel a distance 1 meter, in 1 second it will travel a distance 3 meter. So as seen by this observer, it has progressed the distance of 2 meter in 1 second. So we can say its velocity is 2 meters per second. So we can see with respect to various frames of observation, the motion parameters, like here we are observing velocity of this car, the motion parameters measured are different. So we can simply state a reference frame is a coordinate system with a clock, as all motion parameters are related to time for measurement of time. A coordinate system with a clock for measurement of time. It may be at rest, on ground, or may be attached to a moving body or observer. This is the basic definition for a reference frame. We just go through all the things once again because reference frame itself is a very important concept, because all problems which we are going to face in the chapter of motion in one dimension, motion in two dimension, or any other topic of mechanics, these are all related to reference frames. Now we will study about various kind of motion parameters associated with the motion of a body. The very first is distance and displacement. I hope in your earlier classes you have covered the basic difference between distance and displacement in motion of a body. So a body starts from point A, and along with this path the body goes to point B. This is the path along which the body is moving. So the length of this path we simply call as distance. We just talk about distance covered. This can be written as path length. If we just talk about the term displacement, it is the shortest distance between point A and point B. This point A to B we call a displacement vector, because displacement is a vector quantity. When we talk about displacement, it is simply the straight line length A to B. This AB vector is the displacement vector which is associated with the body. Now, say for one dimensional motion, when we talk in case of a rectilinear motion, when a body moves along a straight line, say it is possible that from a point O a body starts, it moves in forward direction. At some point A it will come to rest, and then it will return back on the same line and reaches a point B. So here we can simply state, when we talk about the distance covered by the body, so this distance we can write as OAB. It goes from O to A, then A to B. The total distance will be OAB. But when we talk about its displacement, this displacement can be written as OB vector. It is directly from a starting point to the end point. This is the vector OB which we call as displacement vector. Now the second point, if we talk about the motion parameters, that is speed and velocity. Speed and velocity are exactly related to the phenomena which we have studied in distance and displacement. When we talk about the speed, it is a scalar quantity and it is measured by calculating the distance traveled by the body in a given time duration. And velocity is a vector quantity which gives which is measured by calculating the displacement covered by the body in a given duration. So if we talk just about the speed, you can simply call it it is rate of change of position of body, and here we measure only the magnitude. But when we talk about velocity, velocity is also given as the rate of change of position, but in case of velocity we must mention the magnitude as well as direction. Without direction the velocity will be incomplete information. It will just be the magnitude of velocity which can be written as the speed. And speed and velocity, these can be defined in various ways. Let's see that in detail. Let us discuss the concept of average speed and average velocity. When a particle moves, average speed in a given motion can be written as total distance traveled divided by time taken. Similarly, we can also define average velocity. For a particle's motion, average velocity can be written as total displacement divided by time taken. If particle is moving in a single direction, then there won't be any difference in average speed and average velocity. Like for example, a particle starts from point A, goes to a point B situated at a distance L, and say at time t1 it was at position A and at time t2 it was at position B, then average speed in going from A to B can be simply written as L by t2 minus t1. And the same will be the average velocity. There won't be any difference in average speed and average velocity. But say in a one-dimensional motion situation is like this, that a particle starts from A, goes to a point B located at a distance L1, and then it comes back to a point C by traveling a reverse distance L2, and say it was at position A at time t1 and at C at time t2. In this situation, if we talk about average speed we write as L1 plus L2 by t2 minus t1. Because in moving from point A to C, the total distance covered will be L1 plus L2 and the time taken is t2 minus t1. And here if we calculate the average velocity can be written as the displacement upon time. So your displacement will be L1 minus L2 and the time will remain same, that is t2 minus t1. This is the basic difference between average speed and average velocity. In average velocity, we must also mention the direction in which it is moving. Like here it is moving from A to C. Let's say the direction towards east. So we can simply state in this direction this is the average velocity which is given in vector form, where we can write this delta L vector which is from A to C divided by delta t, or we must write the magnitude and the direction which is toward east or along positive x-axis. Now we'll discuss the concept of instantaneous velocity. As the name implies, we simply state it is the velocity of a particle at an instant. Practically, it is very difficult to measure the velocity at an instant. Say if a particle is moving in a particular direction, say in the direction of positive x-axis, at a particular instant of time it is at a position x. So we consider a very small neighborhood of this displacement or this motion, say from time t to we consider the time t2 t plus dt, and say in this small duration of dt it has traveled by a distance dx. So it will be able to reach the position from x to x plus dx. So we can consider that at the instant t the particle has covered a distance dx in time dt. So at this time t or at the instant t, instantaneous velocity can be given as, this is given as v is equals to dx by dt. As it is velocity, we define it in vector form. So v vector can be written as dx vector, which is in this direction, divided by dt. So we can simply state it is the rate of change of position with respect to time. This is giving us the instantaneous velocity. Or we can simply write, if we are having the position as a function of time, we can find out the differentiation of position with respect to time to get the value of instantaneous velocity. So we can also write instantaneous velocity is differentiation of position with respect to time. Or we can also write, for a given motion, if position is defined as position x is given as a function of time, then instantaneous velocity is the slope of x versus time curve. As we already studied that this differentiation of a particular variable with respect to its free variable on which it depends, it gives us the slope. Or if y is given as f of x, we have studied that dy by dx is the slope of y equals to fx curve. Similarly, here we can write, if we are having position as a function of time, then instantaneous velocity is given by the slope of x versus time curve. In this example, we are asked that if a particle moves such that its displacement is given as 4t to power 4 minus 3t square plus 7t plus 6, we are required to find the velocity at t equal to 2 seconds. So here the question is almost directly handled just by differentiating the displacement with respect to time. As we know, v is equals to dx by dt. On differentiating, we get 16t cube minus 6t plus 7. And we are required to find velocity at 2 seconds. We can directly put the value of t at 2. This will be 16 into 8 minus 6 into 2 plus 7. So this will be 128 minus 12 plus 7, that is equals to 123 meters per second. So you just keep it in mind directly that on differentiating the displacement with respect to time, we get the velocity. You can also write down a note which gives you a relation in velocity and displacement as differentiation of displacement is velocity. On integrating velocity, we get displacement. We'll also take up some applications based on this. As far as such questions are concerned, where you are just given with the displacement and you are required to find the velocity, you just need to simply differentiate it and substitute the value of time when you are required to calculate the velocity. In this question, we are given that the velocity of a particle is given as v is equals to 3t square plus 2 meters per second. We are required to find the displacement covered by the particle from t equals to 1 to t equals to 2 seconds. Here, in this situation, we can simply write as v is given as 3t square plus 2. We can write v as dx by dt. This is 3t square plus 2. Further, we can write dx is equals to 3t square plus 2 into dt. We just separate the variables, as here the terms of time are there. We just take this dt on the other side. Now we integrate on both sides. We integrate both the sides. You can see dx is a small element of displacement. On integrating this, we get the displacement, and on right hand side the terms of time are there, so we need to integrate it within the specified limits of time. Here you can see we are required to find the displacement covered by the particle from t equals to 1 to 2 seconds. Say at t equal to 1 second, particle was at a position x1, and at t equals to 2 second, particle was at a position x2. So we apply the limits on both sides of equality which are corresponding to each other. Like at 1 second the position, 2 second the position, where it was at t equals to 2. If you integrate this dx, on left hand side it will become x2 minus x1. On right hand side it will become the integration of 3t square will become 3 into t cube by 3. So it will be t cube plus integration of 2 will be 2t. We apply the limits from 1 to 2. So here x2 minus x1, that is the displacement from t equals to 1 to 2, can be directly calculated by substituting the limits. If we put the upper limit, this will become 8 plus 4 minus, we substitute the lower limit, it is 1 plus 2. So this will give us 12 minus 3, that is equals to 9 meter, which is the answer to this question. In this question, we have directly calculated the displacement just by substituting the corresponding limits. In this example, we are given that a body moves at a velocity of v equals to 2t plus 4 meters per second, and we are required to find the average velocity of body from t equals to 1 second to t equals to 2 seconds. We are also given that initially at t equal to 0, body starts from origin, that is x equals to 0. Now in this situation, if we are required to find the average velocity, we need to find the position at 1 second and 2 seconds. Let at time t1 equals to 1 second, position was x1, and at time t2 equals to 2 seconds, the position was x2. Then we can directly state the value of average velocity between time t1 to t2 can be written as x2 minus x1 upon t2 minus t1. So in this situation, this is x2 minus x1 upon t2 minus t1 is 1 second. So our average velocity will just be x2 minus x1. If we are required to find the value of x2 minus x1 in this situation, we can simply use, as v is given as 2t plus 4, here we use dx by dt is equals to 2t plus 4. So this gives us dx is equals to 2t plus 4 into dt, and on integrating both the sides within the corresponding limits, like at t equals to 1 second, position was x1, and at 2 second, position was x2. Then left hand side can be written as x2 minus x1. Right hand side on integration, we are going to get integration of t will be t square by 2, that is t square, plus integration of 4 will be 4t. We apply limits from 1 to 2. On substituting the limits, we are going to get with the upper limit, it will be 2 square is 4 plus 4 into 2, 8, minus we put the lower limit, that is 1 plus 4. So this will give us 12 minus 5, that is equals to 7. So here value of x2 minus x1 is 7. So we can simply state here the average velocity can be written as 7 meters per second, which is the answer to this question. Let's discuss about acceleration. As I think in your earlier classes, you might have covered that acceleration is rate of change of velocity. But here we define acceleration as an instantaneous term. Say for example, a particle starts from a point and moves in the positive direction of x-axis. So at any general instant of time t, the particle is having a velocity v, and in a very short duration from t to t plus dt, so the velocity is increased from v to v plus dv. So we can say in the duration dt, the velocity increment is dv. Then in this situation at this time t, as dt is very small neighborhood of this time t, we can write acceleration time t can be given as this is dv by dt. This is the instantaneous acceleration at time t. This can be simply written as time derivative of velocity vector. Vectorially we find acceleration vector is dv vector by dt. And it can also be written as a slope of velocity versus time curve, because dv by dt is the slope of vt curve if we are finding the acceleration for a body moving in rectilinear motion. From here we can also analyze one thing, as we have studied, if we are having displacement, if we differentiate displacement we get velocity. If we differentiate velocity with respect to time we get acceleration, and vice versa is also true. When acceleration is integrated we get velocity, and when velocity is integrated we get displacement. We are going to discuss several applications or examples based on this concept. Like here instantaneous acceleration we can also give as dv by dt, or if we write velocity as dx by dt, or velocity is the differentiation of displacement with respect to time. So we can write acceleration as second differentiation of displacement with respect to time, that is d square x by dt square. There is one more way in which acceleration can be written, like if it is expressed as dv by dt, which is multiplied by dx and divided by dx. So here you can see this dx by dt. This dx by dt can be written as v into dv by dx. There's another way of expressing acceleration as velocity multiplied by slope of velocity displacement curve. Here we can see acceleration is the slope of velocity time curve. Here you can write acceleration as instantaneous velocity multiplied by slope of velocity versus displacement curve. There's another way of finding the acceleration. As we have seen that acceleration can be given as dv by dt, or it can also be written as v dv by dx. So if there's equation 1, there's equation 2. Both the equations are having their own importance. Like if acceleration is given as a function of time, then we use equation 1, because here you can see acceleration is expressed in terms of velocity as well as time. Sometimes it happens that in various problems, if a is given as a function of displacement, then obviously here we are going to use equation number 2, because here you can see in equation 2 acceleration can be expressed at velocity as well as displacement. Sometimes it may happen that if a is given in terms of velocity, then we can use either equation 1 or equation 2, which basically depends on the requirement of data in the problem, or whatever is required in the problem. Based on that, we are going to use equation 1 or 2, whether it is related to time function or it is related to displacement function. That will be more clear with the help of some examples. Let us take up one example here only. Say if for a particle its displacement is x is equals to 3t cube plus 2t square plus 5t plus 6 meter. Here you can see the displacement is given as a function of time, and say we are required to find acceleration of particle at t equal to 1 second. So if we are required to find the acceleration, we need to differentiate it twice. Like if this is the displacement, here we can calculate instantaneous velocity as dx by dt. So if we differentiate it, it will give us 9t square plus 4t plus 5. It is in meters per second. And if we find out acceleration, it can be further given as dv by dt. So once again we differentiate it, it will be 18t plus 4 meter per second square. So here we are required to find acceleration at t equals to 1 second. That 1 second acceleration can be given if we put t equals to 1, it is 18 plus 4, that is 22 meter per second square. This will be the answer to this question. Now we are going to discuss about average acceleration. We can simply state for a motion of particle between two instants, its average acceleration can be given as, average acceleration is defined as, it is defined under this symbol. It is a total change in velocity divided by time taken. If velocity is changed by delta v, we can simply write it delta v vector by delta t. This is the average acceleration. So if a particle velocity changes from v1 to v2 in a time t1 to t2, it can be written as v2 minus v1 vector divided by t2 minus t1. This is the way how we directly find the average acceleration. For average acceleration, we don't need the way how velocity is varying, how it is changing. We just need the velocities at initial and final instants. Just to understand it, we take up here an example. Say if a truck moving at 4 meters per second toward south, a truck is moving in south direction at a speed 4 meters per second, takes a turn toward east, and say its velocity changes to 3 meters per second. If turning time is 10 seconds, we are required to find the average acceleration of truck. So this is the question we need to solve. In this situation, once again, if you just have a look, the truck was initially moving at 4 meters per second towards south. So if we talk about this v1 vector, v1 say it is the initial velocity, it is 4 meters per second towards south, so it is moving in the southward direction. And it takes a turn toward east. So final velocity v2, which becomes finally 3 meters per second, it is toward east. And we are required to find the average acceleration. So here average acceleration can be written as it is v2 vector minus v1 vector divided by total time taken as 10 seconds here. So v2 vector minus v1 vector, either we can find out by using velocity triangle or vector triangle, like so v2 vector is in this direction, if v1 vector is in this direction, so minus v1 vector will be in this direction. So resultant would be this. You can say this is 3, this is 4, so this will be certainly 5, So if we substitute the magnitude of this v2 minus v1 vector, the magnitude of acceleration can be given as 5 by 10. So here in this situation, it will be 0.5 meters per second square. If we wish to find out its direction will be toward, you can simply state if this is the east direction, it will be north of east at an angle theta. And here tan theta can be written as 4 by 3. That means theta will be 53 degree. This will be in direction 53 degree north of east. You can simply state from the direction of east, it is at an angle 53 degree toward north, and the change in velocity v2 vector minus v1 vector is 5. So v2 minus v1 is 5 and time taken is 10, so 5 by 10. The average acceleration will be 0.5 meters per second square in a direction 53 degree north of east. In this example, we are given that if a car accelerates with an acceleration depends on displacement as a is equals to 6x square plus 2x plus 5, and we are required to find velocity of particle. One, it is at x equals to 3 meter, and we are also given that initially it starts from x equals to 1 with velocity 2 meters per second. Here, if we draw the physical situation, we can say if this is the positive direction of x-axis and this is the position x equals to 1, and it is given that initially at t equal to 0 particle was at x equals to 1 meter and it starts with the initial velocity of 2 meters per second. Now it accelerates with an acceleration a given by this expression. Now we are required to find the velocity when it is at x equals to 3 meter. We can see that acceleration is given in terms of x. So here we use a is equals to v dv by dx. If acceleration is given as a function of time, then we use acceleration as dv by dt. Here it is given in terms of x, so we are using it as v dv by dx. It is 6x square plus 2x plus 5. Further we can write v dv is equals to 6x square plus 2x plus 5 into dx after variable separation. Now we integrate both of these sides corresponding to the limits. Like in the beginning, position x was x equals to 1, which is given to us, and initial speed was 2. We are required to find the velocity v when position becomes 3. So we put the upper limit at 3 on the position side or displacement side. On left side we put the variable v which we are required to find. On integrating this, we are going to get v square by 2. We'll put the limits from 2 to v, and on this side on integrating you can see that integration of x square becomes x square by 3. So it will be 2x cube plus 2 into x square by 2, it will be x square plus 5x, and we put the limits from 1 to 3. So on left hand side we are going to get v square by 2 minus 2 is equals to, first we put the upper limit, that will be 2 into 27 plus 9 plus 15 minus we put the lower limit, that is 1. It will be 2 plus 1 plus 5. You can see here we are going to get the value of v square as 78 minus 8 plus 2. In this situation, is 78 minus 8 plus 2 multiplied by 2. So here we'll get this v square is equals to 72 into 2. So this will be 144. So the value of speed we are going to get is root of 144, that is 12 meters per second. This is the velocity of particle at x equals to 3 meter. In this example, we are given with a particle which moves with an acceleration given as 80 plus 6 meters per second square, and we are required to find the displacement of particle at t equal to 3 seconds. If at t equal to 0, it starts from origin with initial speed of 1 meters per second. Again, let's draw the physical situation. Say particle starts at t equal to 0 with the initial speed 1 meters per second and is having an acceleration a given by this expression. Now in this situation, we are required to find the displacement of particle at t equals to 3 seconds. Now we know well that if we are given with acceleration, on integrating this we get the velocity and on integrating velocity we get the displacement. So here we use dv by dt is equals to 8t plus 6, as acceleration can be written as dv by dt. It can be further written as dv is equals to 8t plus 6 into dt. If we integrate both the sides with the relation at t equal to 0, the speed was 1 meters per second, and at a general time t, velocity is say v. On left hand side, when we integrate it, we'll get v. When we apply limits from 1 to v, it is v minus 1. That will be equal to, when you integrate this, it will be 8t square by 2 plus 6t. So here this gives us the velocity as 4t square plus 6t plus 1 meters per second. This is the velocity as a function of time. Now we are required to find displacement, so we'll further write it dx upon dt. This dx by dt can be written as 4t square plus 6t plus 1, and we can write dx is equals to 4t square plus 6t plus 1 into dt. Now we integrate this expression with the relation that at t equal to 0 particle was at initial position 0 and at a general time t particle is at a position x. So you can see on integrating we get the value of x is equals to, this will be 4t cube by 3 plus this will be 6t square by 2, that will be 3t square plus t. Now we are required to find the value of displacement of particle at t equal to 3 seconds. We just substitute t equals to 3. We can say at t equal to 3 seconds, the position can be given as 4 into 3 cube by 3 plus 3 into 3 square plus 3. So here we are going to get it 4 into 9, that will be 36 plus 27 plus 3. So this will be 66 meter. So this is the answer to this question. And you can see we are using the very common relation which we have studied, that on differentiating displacement we get velocity and on differentiating velocity we get acceleration. So here we are just following the reverse of that. We are given with acceleration. On integrating acceleration we have got velocity, and on integrating velocity we have got the displacement. The only point where you need to be very careful is about the application of limits. The limits must be corresponding on both sides of equality. So be careful about such type of questions. In this example, we are given the instantaneous velocity of particle as v is equals to 5 e to power t meters per second. And we are required to find the average acceleration and average velocity of particle between instants t1 equal to 2 seconds and t2 equal to 4 seconds. We are also given with the initial condition that at t equals to 0, initially the particle was at origin, that is at x equals to 0. Here we are required to find the average acceleration, as we know that average acceleration can directly be given as v2 minus v1 upon t2 minus t1. That is delta v by delta t. So here as particle is moving in rectilinear motion in a straight line, we can directly state v2 and v1 can be given directly by the expression as at 2 seconds the velocity will be 5 e to power 2 and at 4 seconds it will be 5 e to power 4. So it can be directly written as final velocity is 5 e to power 4 minus 5 e to power 2 divided by 4 minus 2. So the result will be 5 by 2 e square into e square minus 1 meters per second square. This is the answer to first part of the question, that is average acceleration. If we find out the average velocity of particle between 2 seconds to 4 seconds, we know well that average velocity can be given as x2 minus x1 upon t2 minus t1, where x2 and x1 are the position of particles at final and initial instants. So we are required to find the position of particles at t1 and t2 times. So these can be written as, here v is given as 5 e to power t, so we can write dx by dt is equals to 5 e to power t. So we can write dx is equals to 5 e to power t dt. On integrating this expression with the initial condition that at t equal to 0, x was 0, say at time t equal to 2 second, particle was at position x1. So here we'll directly get the value of x1, that will be equals to 5. Integration of e to power t will be e to power t. This will be integrated from 0 to 2. So this can be given as 5 e square minus 5, because e to power 2 minus e to power 0 will be 1. Similarly, we integrate the same expression from 0 to 4 second and this from 0 to x2. We'll get the value of x2 as 5. Again e to power t remains e to power t, it will be integrated within limits from 0 to 4. So this will give us 5 e to power 4 minus 5. So we substitute the values of x2 and x1 over here. You can see that average velocity can be given as, this will be, this minus 5 gets cancelled out, it will be again 5 e to power 4 minus 5 minus of 5 e square minus 5 divided by 4 minus 2. So in this situation the result will be 5 by 2 e square into e square minus 1 meters per second. So you just have a look very carefully on the process what we are using, and this is a special function where we can see the value of average acceleration and average velocity are numerically equal. And here to find out the average velocity, we have calculated x2 minus x1. This can also be directly obtained by applying the limits from 2 to 4 and x1 to x2 will directly get the value of x2 and x1, that you can execute in your copy and verify whether you are getting the result or not. Now we are going to discuss the motion analysis with uniform acceleration. So when a particle moves with uniform acceleration in rectilinear motion, we can simply state, say when a particle moves at constant acceleration a and starts with initial velocity u. Say we are required to find velocity at the general time, you can simply state the velocity of particle after time t can be obtained as, we simply write acceleration as dv by dt, and here we can write dv is equals to a dt. Now we integrate this expression. At t equal to 0, we can substitute the limit of velocity was u. In the beginning, it starts with initial velocity u, which was given. At a general time t, the velocity of particles say becomes v. Then on integration, left hand side will become v minus u, and on right hand side we can say, as acceleration is constant, it can be taken out, and it becomes integration from 0 to t, so that will be just t. So velocity after time t can be written as u plus at. So you must be very careful about this equation. Equation number 1 we call first speed equation for constantly accelerated motion. For constant accelerated motion, we can directly use this expression which gives us velocity after time t if initial velocity is u. Further, if we are going to use the same expression, like say we write, further we use, if we are given as v is equals to u plus at, we can simply write v as dx by dt, which is u plus at, and we can write dx is equals to u plus at into dt. This gives us the displacement travel in a duration dt. If we want to calculate the displacement after time t, so we can say initially when time was 0, the displacement was 0 when the particle was just started, and a general time t particle will be at a position say s. Then on integration we'll get integration of dx, that will be s, and if we integrate u plus at, then u and a are constant, so it can be written as ut plus at square by 2. So this s is equals to ut plus half at square. This equation, which is equation number 2, this gives us the displacement covered by the particle in a time t if it is moving at constant acceleration a and with initial velocity u. This equation we term as second speed equation for uniformly accelerated motion. Let's discuss another equation, that is speed equation number 3 or third speed equation for uniformly accelerated motion. Similarly, if we use acceleration as v dv by dx, here we can write v dv is equals to a dx. On integrating this expression, say from a starting point where displacement was 0 and velocity was u, say after covering a displacement s, say velocity becomes v, then on integrating we'll get the final velocity after traveling the displacement s. So here it will be v square by 2, and we apply limits from u to v, and on right hand side we get a into s. So here left hand side will become v square minus u square by 2 is equals to as, or we can write v square is equals to u square plus 2as. Here this equation gives us the velocity of particle after covering a displacement s if it was moving with a uniform acceleration a and with the initial speed it was started with u. This equation we write third speed equation for uniformly accelerated motion. Let's discuss the displacement of a particle during nth second for uniformly accelerated motion. Say for example, a particle starts from time t equal to 0 and is moving in a rectilinear motion. Say we talk the time from t equal to 0 to t equal to 1 second. This we can call as first second of motion. From time t equals to 1 to t equal to 2, again the duration is 1 second, this we call second of motion. Similarly, from t equals to 2 to t equals to 3, it is the third second of motion. Similarly, we can define different motions. If a particle starts with the initial speed u and it is accelerating with acceleration a, so we can say after every instant its velocity is gradually increasing. So as it is gradually increasing, we can state that later on after starting, in 1 second duration, particle will cover more distance or displacement compared to the initial duration of 1 second. Say if we find out the displacement covered in nth second of motion. So nth second of motion, if say particle cover a displacement delta Sn, it can be written as displacement covered up to n second minus displacement covered up to n minus 1th second. So we just subtract the displacement up to n minus 1th second from the displacement which is covered up to nth second. So it will give us the displacement delta S which is covered during nth second. Because if we talk about nth second, so this is the time from t equals to n minus 1 to t equals to n. So for calculation of this displacement covered in nth second, we are finding the displacement in n second and n minus 1 second, and we are taking the difference. So this can be easily calculated by speed equation number 2, that is ut plus half at square. For nth second, we can write it un plus half an square minus, we subtracted the displacement up to n minus 1 second, this u into n minus 1 plus half a into n minus 1 whole square. When we open this term, we'll get un plus half an square is minus un plus u. Then we are getting minus half an square, then minus half a plus an. So here, if you just carefully have a look on it, this half an square gets cancelled out, this un gets cancelled out. What will be left over is u plus, we can take half a common. This will be half a into 2n minus 1. This is the relation used for calculation of displacement covered by the particle during nth second. This is also a quite important relation, so just keep it in mind. In various problems it is going to be used directly. Now let's write down a note which will be extremely helpful for us to analyze speed equations in various problems. In this note, we are going to write all these speed equations are vector equations and the motion parameters like displacement, velocity, final velocity, initial velocity, acceleration are taken with appropriate signs according to the reference frame chosen. So always be careful while applying the speed equations in various cases. These all are to be used as vector equations, as using these equations as vector equations will always be a beneficial way to handle a problem. And by this method, using this vector equations, we can also reduce the length of solution of a problem. Like if we talk about these equations, the first equation we use as v is equals to u plus at. The second equation is s is ut plus half at square. Third is v square is u square plus 2 a dot s. And the fourth, which we can use, we have just now derived, that is a displacement in nth second, that is u plus a by 2 2n minus 1. So be careful about these equations. In various cases, we are going to use these equations as vector equations. In this example, we are given that a car is moving at 20 meters per second. The driver applies the brakes, which causes a retardation of 4 meters per second square. Find the distance traveled by the car before it stops if the reaction time of driver is 0.4 seconds. The very first thing is you must know about the reaction time. The reaction time you can simply define as the time taken by a human to execute the action after one sees a need of it. In our case, if we talk about the driver, when he sees the need to apply the brakes on, if his reaction time is 0.4 second, that means after 0.4 second, he'll push the pedal of brakes. So till 0.4 second, the car will move with a uniform speed and then the retardation will be applied to the car. So if this is the car which is moving at a velocity of 20 meters per second, we can say at t equal to 0, he sees the need to apply the brakes on. So we can say up to 0.4 second, the car will travel at the same speed of 20 meters per second. Till t equals to 0.4 second, it will move with the same velocity and then the retardation will be applied, that is 4 meters per second square. And due to this, now the car will be retarded and finally the car will come to rest after some time by covering some distance. In this situation, if we find out the first part, when the driver's reaction time was going on, the distance traveled s1 can be written as this velocity multiplied by the time, as it was moving at a uniform speed. So it is simply 8 meters. If we find out the second part of this journey, that is the retarded motion after application of brakes, this distance s2 can be calculated by using the speed equation vf square is equals to u square plus 2as. Here final velocity is 0, initial velocity was 20, acceleration was minus 4, as it is retarded, we can write minus 8 s2, the distance we have taken as s2. So in this situation, the second displacement s2 can be simply given as 400 by 8, it is 50 meter. So this s2 is equals to 50 meter. So answer to the question is we are required to find the total distance traveled by the car, that is s1 plus s2, it will be 8 plus 50, this is 58 meter. This will be the answer to this question. In this example, we are given that a particle starts at initial speed of 17 meters per second and it retards at 2 meters per second square. And we are required to find the distance covered by the particle in 9th second of motion. We just draw the physical situation in this question. We are having a particle at t equal to 0, it starts with an initial speed of 17 meters per second and is retarded with an opposite acceleration of 2 meters per second square. So gradually its speed will decrease, and after some time its final velocity becomes 0. And we can easily calculate the time at which its final velocity is becoming 0. Say this time is t1. So we can simply write the equation v final as u plus at. So here 0 can be written as 17 minus 2 t1 because acceleration will be minus 2 in this case. So here we can see the time t1 we are getting is 17 by 2, that is 8.5 second. So at t1 equals to 8.5 second, it is coming to rest, and then it will return back because acceleration was opposite. So till this point, what will happen? Its velocity is retarded, it will come to rest, and then it returns back due to the continuous action of acceleration, and now it will be in an accelerated motion. Now in this journey, we are required to find the distance covered by the particle in 9 seconds of motion. If we calculate the distance by using the formula for displacement of nth second or displacement of particle in nth second, just see what will happen. You'll be able to have a look on an interesting result. The formula for nth second of motion was u plus a by 2 into 2n minus 1. So here we are required to analyze the motion in 9 seconds. So we find out the displacement in 9 seconds of motion. This will be 17 plus a by 2. This will be minus 2 by 2 into 2 into 9 minus 1. Just see what you are getting. This 17 minus, this is 1, and this 18 minus 1, 17. The result is 0. Now it is quite a surprising result how it is possible that displacement becomes 0. Yes, it is possible because you can see we are required to analyze the motion in 9 seconds. So 9 seconds will be the duration from t equals to 8 to t equal to 9 seconds of motion. This is the 9th second. So we can see at 8.5 seconds, the particle was at rest. It is the extreme position. So if it is at this position at t equal to 8 seconds, it will take 0.5 seconds in going from this point to this point. And similarly, as we analyze the accelerated motion with same acceleration, it will take same time, that is 0.5 seconds going from this point to this point back. So here it will reach at t equal to 9 seconds. So you can see at t equals to 8 and 9 seconds, the particle was at same position. That's why the result is coming out to be 0. Because this is the formula for displacement in 9 seconds. It is not giving us the distance. And in the question, it is asked to find the distance covered. So that we can easily calculate by finding out the distance covered by the particle from rest within 0.5 seconds, and we make it twice. So if this distance is s1, this s1 can directly be written as half at square, as initial speed here is 0. So this is half into 2 into 0.5 whole square. So this is 0.25 meter. So we can directly write distance covered in 9th second is this 2s1, that is equals to 0.5 meter, which is the answer to this question. So be careful about such type of questions which are slightly tricky, but several times it happens that students without any analysis or without any thinking, they just apply the direct formulas and they ignore such type of language in the question. So be careful in future about such type of questions. In this example, we are given that a car and a truck starts from same point along same direction. A car with initial speed of 2 meters per second and acceleration 2 meters per second square, and a truck with a constant speed of 20 meters per second. We are required to find the time after which car will overtake the truck. Now in this situation, again we first draw the physical situation. So if this is the car and this is the truck, we are given that car starts at an initial speed of 2 meters per second and it is accelerated with an acceleration of 2 meters per second square. And the truck continuously moves with a constant speed ut is equals to 20 meters per second. So obviously, as initially truck is moving fast compared to car, it will be moving ahead of the car, but due to acceleration, car will speed up, and at some point of time, the car will be able to overtake the truck. So there will be a time when their displacement will again become equal. So if we find out the displacements, say this is the time t naught at which again displacement becomes equal. So we can find out displacements. For truck, you can simply write, as it is moving with a uniform velocity, the displacement of truck can be written as 20 into t naught, that is velocity into time. For car, if we find out the displacement, the displacement of car can be written as initial speed is 2, acceleration is 2. It is ut plus half into a into t square. This we are going to use. Now, obviously for overtaking, we can write displacement of truck is equals to displacement of car. So if we equate the displacements, we'll get 20 t naught is equals to 2 t naught plus t naught square. Here one t naught gets cancelled out and directly we get the value of t naught as 18 seconds. This is the answer to this question. So this time t is equals to 18 seconds when car will overtake the truck. In this example, we are required to find the ratio of distances traveled in first second and third second by a particle started from rest with uniform acceleration. In this question, say if a particle starts from rest, that means its initial speed is 0. as it is moving with uniform acceleration, let us assume its acceleration is a. If it starts at t equal to 0, then say from t equal to 0 to t equal to 1, it covers a distance s1. So this s1 is the distance covered by the particle in the first second of motion. And then from t equal to 1 to t equals to 2, whatever distance it will cover, say it is s2. Then the s2 is the distance traveled by the particle in second of the motion, because first second is from 0 to 1, second of motion is from t equals to 1 to 2. Similarly, for third second of motion, we can take it from t equals to 2 to t equals to 3. Say if this distance is s3. So we are required to find the value of s1, s2, 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 s3. This value we are required to calculate. So I suppose all of you can recall the direct expression for finding the displacement covered by the particle in nth second. The displacement covered in nth second can be written as u plus a by 2 into 2n minus 1. So here our initial velocity is 0, so we can directly calculate the distance traveled in the first second of motion as a by 2 into 2 minus 1. So its value is a by 2 only. If we find out this s2, that is in the second of motion, again u is 0, we take a by 2 into 2 into 2, 4 minus 1, it is 3. So it is 3a by 2. We find out the distance traveled in the third second of motion. So we can write it a by 2 into 2 into 3, 6 minus 1 will be 5. So this will be 5a by 2. So in this situation, our ratio s1 is to s2 is to s3 can directly be written by these values as 1 is to 3 is to 5. This is the answer to this question. Now we'll study free fall motion. We can simply state that the motion of a body moving freely under Earth's gravity is called free fall motion. When we talk about free fall motion, we can simply state under free fall, acceleration is always taken as g in downward direction. Well, we know very well that if there is a ground and the body is released above the ground, it will experience a downward force which is equal to the weight of body, and due to the weight it will fall with an acceleration g. So acceleration of freely falling bodies near the Earth's surface are always considered as freely falling bodies having constant acceleration g in downward direction. In all the speed equations, we can replace the acceleration by g. Like if we take downward direction positive, if we take downward direction positive, then what we'll do, we can always use g in downward direction, so it will remain positive. So speed equations can be written as v is equals to u plus gt, s is equals to ut plus half gt square, v square is u square plus 2gh, or delta h, distance traveled or height covered in another second, can be written as u plus g by 2 into 2n minus 1. Now if we take upward direction positive, if we are taking upward direction as positive, in that case acceleration we consider as minus g. In this situation, acceleration is positive g, because downward direction we are taking positive. When a body is moving down, it will be accelerating. Similarly, if we take upward direction positive, when a body goes up, the acceleration will take as minus g, or we consider it the body to be retarding. So in this situation, we write the equation as v equals to u minus gt, s is equals to ut minus half gt square, v square can be written as u square minus 2gh, and height traversed in another second can be written as u minus g by 2 into 2n minus 1. These are the speed equations we can use for free fall motion, depending on in which direction we take positive direction of our reference frame. So the use of these speed equations depend on the choice of reference frame as well as the direction where we are taking it positive. In this example, we are given that a boy throws a ball up at a speed u, and we are required to find the time to reach its maximum height and the maximum height attained. So if we draw the physical situation in the question, we can state on ground there is a boy who throws a ball in upward direction at a speed u. We know well that when the ball goes up, it will be retarded in downward direction with acceleration g. So after some time, its final velocity is going to be 0, and certainly it will reach a maximum height h before its velocity becomes 0. So in this situation, if we find out the time to reach maximum height, say if it was thrown at t equal to 0 and say at time tf it reaches the maximum height, so we can use, here we use v is equals to u plus at. Here final velocity we can take as 0, initial velocity we take as u. As acceleration is opposite to velocity, we can write acceleration as minus g, and the total time to reach maximum height is tf. So here this tf can be written as u by g. This is the answer to the first part of this question A. If we wish to find out the maximum height attained, now we can use directly v square is u square plus 2as. In this situation, again the final velocity will be 0, the initial velocity is u plus we take again acceleration as minus g into the maximum height we can take as h. On solving this, you can see the maximum height can be written as u square by 2g. This is the answer to the second part of the question. So always you should keep these two results on your tips, because in several cases these are going to be used directly. When a particle is thrown up, it will take a time u by g to reach the maximum height where final velocity becomes 0, and the maximum height it will reach will be u square by 2g. And obviously it will not remain at rest over there, again it will fall. So it will take same time in coming back down. So if we find out the total time of flight in going up and then coming down, this total time of flight can be written as 2tf, or it is 2u by g. This itself is a very important result you should keep in mind. In several questions these results are going to be used directly. In this question, we are given that a stone is released from rest from a height above the ground. It covers a distance of 6 meters in last second of its motion. We are required to find the height from which the stone was dropped. Again, if we draw the physical situations, this is the ground, and from some height, say h, the stone was dropped at t equal to 0. Say if it falls for n second, then in the last second of motion, that is from n minus 1 to n second, the distance covered by the particle is 6 meters. And we are required to find the height h from which it was dropped. So again, we just analyze the same. Let stone falls for n seconds. This implies we use the relation of distance covered in the nth second. So in nth second, the distance or displacement covered can be simply written as delta Sn is equals to u plus a by 2 into 2n minus 1. So here this will be delta Sn, which is equals to 6. It can be written as initial speed here is 0, and it is falling with an acceleration equals to g. Here we'll write g by 2 into 2n minus 1. So in this situation, if we put g is equals to 10 meters per second square, we are going to get 2n minus 1 is equals to 6 by 5. So this gives us n is equals to 11 by 10 seconds. So as the value of n we are getting 11 by 10 seconds, we can easily calculate the total height to which the stone has fallen. Now the total height, this can be written as directly half gt square, as initial speed is 0, h can be written as ut plus half at square. This will be half into 10 into 11 by 10 whole square. This will give us 121 by 20 meter. This will be the answer to this question. Let's see the concept of relative motion. This concept of relative motion is basically linked with the type of observer or observation. Observation with respect to a given reference. When we talk about a reference, we have already studied that a reference frame may be considered to be at rest or may be considered to be in motion. So when a motion of a body is observed with respect to another body or another observer, that motion we simply call as relative motion. So we discuss about two cases of relative motion. Here we are mainly studying the rectilinear motion or motion in one dimension. So we consider our cases of rectilinear motion only. Say we are having two bodies A and B. Say A is moving with a velocity v and B is moving with a velocity vb. In this situation, if we talk about velocity of B with respect to body A, or when A measures the velocity of B, what velocity it is going to measure. So here we can see velocity of body B with respect to A. When we measure it, it is simply vb minus va, because B will cover a distance vb in 1 second and A will cover a distance va in 1 second. So from as measured by body A, when we observe the body B, we can say its motion by which the B is progressed forward will be vb minus va. So in 1 second, body B can be considered to be progressed by a distance vb minus va with respect to body A. So this vba we simply term as relative velocity of body B with respect to body A. So always remember, when two bodies move in same direction, velocity of one body with respect to other can be written as difference of their velocities. So this is a case 1 which we consider when bodies move in same direction. Similarly, we can consider a case 2 which we consider when bodies move in opposite direction. When the bodies move in opposite directions, the situation is like this body A and this body B, and they are moving toward each other, say with the velocity v and vb. In this situation, when from body A it is observed that how body B is moving, we can say that B will come closer to A by velocity or with velocity vb plus va, because in 1 second A will travel a distance va and B will travel a distance vb. When A will observe body B, the separation will decrease by va plus vb. So with respect to A, body B appear to be coming toward A with the velocity Vb plus Va. So here velocity of body B with respect to A can be written as Vb plus Va. So always remember that when bodies move opposite to each other, or even when they are moving away from each other, when the velocity directions are opposite, we can say the relative velocity is the sum of the two velocities. And when bodies are moving in same direction, we can state that the relative velocity of one with respect to other is the difference of the velocity. So always remember these two concepts as it is, because in various questions we are going to use these directly. Along with this, we can also write that same concept of relative motion can be applied to acceleration of bodies also. That means if two bodies are moving in same direction with accelerations A and AB, then their relative acceleration can be written as AB minus AA. And if they are moving opposite to each other, their relative acceleration will be the sum of the two accelerations. Let's discuss these concepts in some examples. Let us take an example. Here we are given with a tower of height 100 meter, and there are two boys A and B. One is at the top of the tower and other is standing below the tower. And we are given that in the situation shown in figure, if both the boys throw the balls at the same time, find the time when the balls will collide. So in this situation, if we have a look on the motion of both the balls, the upper one is thrown downward at 20 meters per second and the lower one is thrown up at 5 meters per second. They are thrown towards each other. The best way to handle this question by using relative motion, and we consider ball A to be at rest. If we consider it to be at rest, then from this ball A, if we just look at ball B, it is observed to be thrown at a speed of 25 meters per second. As we have studied that when balls move or two bodies move opposite to each other, the relative velocity will be the sum of the two velocities. So in this situation, if we find out the relative velocity of B with respect to A, velocity of ball B with respect to A can be written as 20 plus 5, this is 25 meters per second. If we talk about the acceleration of the balls, you can see it is coming down at an acceleration g and it is also coming down at the same acceleration g. So your relative acceleration of B with respect to A can be written as g minus g, it is 0. As their accelerations are in same directions, the relative acceleration will be the difference of the two, it is 0. So if the ball B is moving at a velocity 25 meters per second downward without any acceleration, we can directly find out the time when B will meet A is, this time can be directly written as distance upon velocity. So it can be written as 100 divided by 25, this is 4 seconds. So we can simply state if at t equals to 0 both the balls are thrown simultaneously, then at t equal to 4 seconds the balls are going to meet somewhere between the initial positions of A and B. So this will be the answer to our question. Let us take up another example where it says two cars moving toward each other at velocities Va and Vb are at a separation d. Say if we are having two cars A and B which are at a separation d and they are moving toward each other with velocities Va and Vb. At this instant, both are retarded with accelerations AA and AB respectively. Say for example, both the drivers of the cars apply their brakes. It is retarded with an acceleration AA and it is retarded with the acceleration AB. We are required to find the minimum value of D such that no collision occurs. Again, in this particular question, it can be very easily handled. We can handle it very easily by using relative motion. Say for example, we consider B at rest, or we analyze the motion with respect to this car B. Then we can say velocity of car A with respect to B, we can simply write as VA plus VB as they are moving towards each other, and as seen from B, the velocity of A appears to be VA plus VB. Similarly, we find out acceleration of A as seen from B. A is moving toward B, but it is having acceleration opposite to VA, and B is also having acceleration opposite to VB. So we can say as seen from B, A appears to be retarded with an acceleration AA plus AB. So its acceleration will be negative of AA plus AB. And with this acceleration, the velocity of A will be retarded. And we want that just before touching to B or colliding to B, the velocity of A should become 0 with this retardation. So here if we use the speed equation, V square is equals to U square plus 2AS. Here we can say final velocity of A should become 0 just before it will hit B. And its initial velocity we can write as VA plus VB whole square. Acceleration we can use negative, it is twice of AA plus AB, and the distance it has to cover is D. So here we can see the value of D will be VA plus VB whole square divided by twice of AA plus AB. If distance is more than or equal to this, A is not going to hit B or no collision will take place if the minimum value of D is this. So this should be the minimum value. If more than this is there, certainly A will be coming to rest before touching to B. In this example, we are given with a balloon which is rising up at 20 meters per second and a stone is released from it when it is at a height of 100 meters above the ground. Find the time after which the stone will hit the ground. If we just draw the physical situation, we can see we are having a balloon. So this is a balloon which is at a height 100 meters above the ground. So this is the ground, and at this position when it is going up at 20 meters per second, someone in the balloon releases a stone. When a stone is released, we all know that from a moving body, when a body is released, it carries the same velocity as that of the moving body. So the stone would be having the initial velocity in upward direction, that is 20 meters per second. So first the stone will move up and then finally it comes down and finally it will hit the ground. We are required to find the time after which the stone will hit the ground. If at t equal to 0, stone was released, first it will move up and finally say at t is equals to capital T time, it is going to hit the ground. Now to calculate the situation, we just analyze its motion. From a starting point, if we just put a reference frame where upward direction we consider as positive x-axis and downward as negative x-axis. So in this situation, the initial velocity of the stone we can write as positive 20 meters per second. We find out the total displacement of particle, its displacement h can be written as minus 100 meter. Throughout the motion, it was having an acceleration g in downward direction. G we can take say 10 meters per second square, which is in the direction of negative x-axis. So acceleration we can consider to be minus 10 meters per second square. Now we use the relation h is equals to ut plus half at square. In this situation, we can write it minus 100 is equals to 20t minus 5t square. Here capital T we are taking the time in which the particle will cover the total displacement from a starting point to the bottom point, which is the time when the ball or the stone will hit the ground. So in this situation, we are having a quadratic equation can be rewritten as t square minus 4t minus 20 is equals to 0. On solving, we just get t is equals to 4 plus minus root of 16 plus 80 divided by 2. So this will give us 2 plus minus half root of 96, which gives us 2 plus minus root of 24 second. Here negative sign can be ignored because time can never be negative. So here final answer will be 2 plus root 24 second. This is the value of time, which is the answer to this question, the time which the stone will take in reaching ground from the initial position of balloon. In this example, we are given that inside a lift which is accelerating up at 2 meters per second square, a loose bolt falls from its ceiling. If height of the lift is 2 meters, we are required to find the speed of bolt with which it hits the floor. We are also given that initial speed of lift is 5 meters per second in upward direction. If we just have a look on the physical situation, if this is the lift, it is moving up at 5 meters per second and its acceleration is say 2 meters per second square. And we are also given with the height of lift that is 2 meters. We are given that from the ceiling of lift, a bolt falls. Now, when bolt is detached from the ceiling, this bolt will also have an initial speed of 5 meters per second because it was attached with the lift, which was moving at 5 meters per second. And after detaching from the lift, it will be in a free fall motion where it will have a downward acceleration g. We are required to find the time when it is going to hit the floor. Actually, lift is moving up also, so it will hit the floor somewhere here. But if the same bolt is observed by an observer who is inside the lift, he'll feel that when the bolt is detached, it starts falling freely with initial speed 0. So we can say initial speed of bolt as seen from lift or with respect to lift is this initial speed is 0. If we calculate the acceleration of bolt as seen by this observer, we can say the bolt is falling freely with an acceleration g and lift is going up with an acceleration 2 meters per second square, which is opposite to g. So if we find out acceleration of bolt with respect to lift, the acceleration of bolt with respect to lift will be, this will be g plus 2, that is 10 plus 2, it is 12 meters per second square. Now relative to lift, if we find out the time at which it is going to hit the lift, say it is t1, so we can simply use in reference of lift, we can write h is equals to ut plus half at square. In this situation, the height is 2 meters, initial speed is 0, so it is half acceleration we take as 12 into t square, say time taken as t1. So from here you can see the value of t1 square we are going to get, this will be 6, 2 by 6, it is 1 by 3. That means the time at which the bolt will hit the floor will be 1 by root 3 second. At t equal to 1 by root 3 second, the bolt will hit the floor. Now in this duration, we can easily find out what velocity it will gain. So if we find out velocity of bolt as seen from lift, if the observer who is inside the lift will be looking onto the bolt, say if it is hitting the velocity with say v1 with which it will hit the floor. So we can simply write v1 is equals to u plus at. So in this situation we'll take u as 0, so this will be just at, that will be 12 into 1 by root 3 second, that will be 4 root 3 meters per second is the velocity of bolt in the reference frame of lift which this observer will see. If we find out the net velocity with respect to ground with which it is going to hit the floor of lift, say it is v2, again we use v is equals to u plus at, but in this situation we take u to be 5 meters per second, because when we observe the bolt from ground it appears to be moving up with 5 meters per second and finally hit the floor in downward direction. So here we take it 5 minus acceleration, we take only g, it will be 10 into t is again 1 by root 3 second, because time remains same in all references which we have studied till now. So it will be 5 minus 10 by root 3 meters per second. So these are our answers to the question. And here we can say in this question, as we are just required to find the speed of bolt with which it hits the floor, so our answer will be 5 minus 10 by root 3 meters per second. But in some case we are required to find the velocity with which bolt will hit the floor as seen from the lift or in the reference frame of lift. Our answer will be 4 root 3 meters per second.
Dear students, now we are going to use graphical analysis of motion. As we are studying rectilinear motion, in rectilinear motion, 3 types of graphs are used in motion analysis. We'll see that these graphs are quite helpful in solving various kind of problems of rectilinear motion also. These 3 types of graphs are displacement versus time graph. The second is velocity versus time graph. And the third is acceleration versus time graphs. We also discuss the variant of displacement time graph as distance time graph. We'll also discuss distance versus time graph. We'll also discuss the speed versus time graph, because some particular category of problems are also asked on distance and speed versus time graphs. But we don't need to spend much time on these at slight variations of displacement and velocity time curves. Let's discuss these one by one. Now, if we talk about displacement versus time graphs, these are also known as position versus time graphs. There's no difference between position versus time and displacement versus time graphs. Say for a given rectilinear motion, we draw the displacement time curve like this. So this is the curve according to which the position of a particle varies with time. So its function is given as x is equal to f of t. In this situation, at any instant of time t, we can directly get the position of particle by using this curve or by substituting the value of time in this function. So if this point is p, we draw a tangent of this curve at this point p and say it makes an angle theta with the time axis. So we can simply state the slope of the curve at point p can be written as dx by dt, which is equal to tan theta. And we all know that dx by dt can be directly written as instantaneous velocity of the particle at this position p. So by a displacement time graph, at any point if we want to calculate or we want to evaluate the instantaneous velocity of the particle, we just need to find out the slope of the curve at that point, and the slope will directly give us the instantaneous velocity of the particle at that point. So in this situation, we can see that this tangent makes an acute angle with the time axis. So here we can simply state the velocity Vp, which is tan theta, will be a positive quantity. If we talk about the decreasing part of the curve at a point Q, if we consider a tangent, you can state this angle theta dash will be an obtuse angle. So at point Q, the instantaneous velocity can be written as tan theta dash, and tangent of the obtuse angle can be written as a negative physical quantity. So in the decreasing part of curve, we can say with time the displacement is coming down or displacement is decreasing. Or as if we talk about the position of particle, it is moving towards origin. So we can state vectorially the velocity will be negative. We can also talk about various situations, like for a practical situation, if say a particle moves in such a way that first it accelerates, then it moves uniformly, and then say it retards. Initially say it was at rest, and finally also say it will come to rest. So first it accelerates, its velocity increases, then it moves uniformly, and then finally it comes to rest. Now in such situations, if a particle is accelerating, we can simply state the slope will first increase and then it moves uniformly. That means its slope remains constant, because you can see the slope is giving us the instantaneous velocity. And if it retards, that means the slope decreases and finally it becomes zero. So if we draw the displacement time graph of such a motion, we can state first the slope is increasing, the curve goes like this, you can see continuously the angle which the tangent makes with the time axis is increasing, and then say for a time t1 it is accelerating, and from time t1 to t2, or you can say for a duration t2, it moves uniformly, so we can draw a straight line. So here the whole slope for the duration t2 remains constant, then it retards. So you can simply draw a curve like this, which is for another duration, say t3. Now in this equation, finally you can see the slope becomes 0, and earlier also slope was 0. This is the curve which is representing a motion where a particle first accelerates, then moves uniformly, and then retards. Similar to this, if we just consider an experimental situation like say the positive direction of x-axis, from origin a particle starts, it moves with a velocity v, it goes up to a particular position in a time t1, then for a time t2 it remains at rest over there, and then it comes back to origin with the same velocity v in a time t3. So from 0 to t1 it was moving uniformly up to this position, say we write maximum displacement xm. For a duration t2 it remains at rest, and then for at time t2 it will start moving in opposite direction, and at time t3 it comes back. Now if we draw the position versus time graph for this motion, you can simply state at t equal to 0 particle starts with a uniform velocity. Uniform velocity means the slope remains constant. Here we can write tan theta is equals to v. This was the time t1 for which the particle was moving uniformly. Then you can state up to time t2, or for the duration t2 minus t1 it remains at rest, so its position remains constant, that is at xm, and then it will start coming back. So the velocity is in opposite direction, or we can say when it was moving toward right, velocity was positive, and now velocity is negative. So it comes down, and at a time t3 it will reach the original position back. So you can simply state again x becomes 0, and say this angle is theta dash. So we can again write tan theta dash is equals to v. Now this angle will be 180 minus theta, and we can state the tangent of obtuse angle is negative. So this angle theta dash can be directly taken as the angle by which we can directly calculate the negative slope. So this is the curve which is drawn for uniform motion, then rest for some duration, and then again uniform motion in opposite direction. Now if similar, this is the curve which we call as position time curve or position time graph. If a similar graph is drawn for distance time, let us draw distance time graph for the same motion of particle when it is moving, then taking rest, and then coming back. So you can simply state, if we talk about displacement, it first increases to xm and then decreases to 0. But when we talk about distance, we can state distance is continuously increasing, because from here to here the distance is xm, and when it comes back the total distance traveled by the particle will become 2xm. The only difference in position time and distance time graph can be taken that distance time graph, if this is taken as distance time graph will never come down. Say it will first increase to a position of xm for a time t1, then it remains at rest up to a time t2, and then again it returns back. But if we talk about position, it is coming down, but if we talk about distance, it is still increasing. So the same graph can be drawn in reverse direction. So up to a time t3 it will be able to cover a distance of 2xm. This is the distance time graph for the same motion. You can simply state, if we are having a displacement time graph, then for those portions of displacement time graph where the curve is coming down, you can draw the mirror image with respect to time axis in upward direction, that will become distance time graph. If we talk about velocity time graphs, these are the graphs relating velocity with time. Say we draw a graph in velocity and time for motion of a particle. This graph is drawn for the function of velocity, how it varies with time. At any position of this graph, similar to that of displacement time graph, here if you draw a tangent and you find out the slope of this graph, say at point x, we can simply state this point is relating time with the velocity. And here the slope can be written as dv by dt, or it can be written as tan theta. And here the slope is giving us the acceleration of particle at the position x. So always remember that the slope of velocity time graph gives us the instantaneous acceleration. And if a slope is positive, like here you can see acceleration at point x, it is tan theta, and theta is acute angle, this can be taken as positive acceleration. Positive acceleration means the velocity and acceleration have same direction, and you can simply state the speed of particle is increasing, or the magnitude of velocity is increasing in this case. When we talk about the decreasing part of the curve at any position, if we draw a tangent, you can see the angle theta dash is obtuse. So this is the point y. So we can say acceleration at point y will be tan theta dash, which is a negative quantity. So here you can see the velocity is decreasing, so acceleration we consider to be negative. So be careful about this situation where we are finding the slope of velocity time curve as acceleration. Along with this, we have already studied in calculus that area under a curve can be given by for between two coordinates on time axis, say t1 and t2. If we find out the area of this curve, So area under the curve can be given as integration of v dt from t1 to t2. Here you can see this integration of v dt will be given as displacement only, because if we talk about v into dt, it is the displacement covered by the particle during the time dt. So if we calculate the total displacement of particle from point t1 to time t2, it can directly be given as integration of v dt from t1 to t2. It will give us the displacement of particle from t equal to t1 to t2. This is another advantage of using velocity time graph, that from velocity time graph using slope we can find out the instantaneous acceleration of particle, and finding out the area under the curve. Like say we find out this area by using integration, this area under the curve gives us the displacement of particle between two given time instants in the given situation. If we just have a look on the motion situation as shown in the velocity time graph, a particle moves in such a way that t equal to 0, its initial velocity was 0. First velocity increases, that means it was accelerating, and then after some time it decreases, and again it becomes 0 at time t1. Then velocity becomes negative. You can say this is the negative direction of velocity, and velocity becomes negative, that means particle has returned in opposite direction, and at time t2 again its velocity becomes 0. So in such situation you can say from time 0 to t1, the area between the curve and the time axis is above the time axis is positive, and from time t1 to t2 you can see that this area is below the time axis, so this is written as negative. Say this total area is s1 and this total area is s2, so we can state total displacement of particle from t equal to 0 to t2 is, total displacement can be written as s1 minus s2. But when we talk about distance traveled, you can always write distance traveled is equals to s1 plus s2, because s1 is the distance traveled in positive direction and s2 is the distance traveled in opposite direction. So displacement will be s1 minus s2, but when we talk about distance traveled it will be s1 plus s2. So be careful about such situations while drawing velocity time curves. Similar to this, we can also talk about acceleration time graphs, but there is nothing much to discuss about acceleration time graphs. Like if we draw acceleration time graph for a given motion, you can simply state an acceleration time graph. If we find out the slope, that a slope will give us the rate with which the acceleration is varying, which is not of much importance in our limitations or the syllabus we are analyzing the things. But when we talk about the area under the acceleration time curve, or area between the acceleration time curve and time axis between two instants t1 and t2, certainly it is of quite importance. Like if we find out this area is say a, so this a can be written as integration of a dt from time t1 to t2. This a dt will give us net change in velocity of particle from t1 to t2. This is something which is important for us to keep in mind, that integration of a dt from t1 to t2 gives us the net change in velocity of particle in going from time t1 to time t2. This you should always keep in mind.
Dear students, now we'll see various cases of displacement versus time graphs. First, we'll analyze these three graphs which are shown here. The very first graph you can see, when we talk about displacement versus time, it is a horizontal straight line. So if we talk about the slope of this line, it is obviously 0. So here we can write the velocity of particle is 0. That means this directly denotes the particle at rest. Whenever a particle is at rest, its displacement time graph will be a horizontal straight line. If we talk about this situation 2, where we can see again it is a straight line at every position, if we find out the slope, its slope remains constant. So in this situation, the velocity of particle can be written as tan theta, which is positive. So it is a motion of a particle which is having positive velocity, or we can state a particle moving away from origin. I've written away from origin because you can see with time the position or x coordinate of particle is increasing, and at every point its slope is constant, or at every point it makes constant angle with the time axis. So particle is moving uniformly. So you can state particle moving away from origin at constant velocity. So this is the way how we analyze such type of graph, where there is a straight line having constant slope or constant angle with the time axis. If we talk about this third case, we can state here the angle made by the line with the positive direction of time axis is obtuse. So here if we find out the velocity, still it is tan theta, but it comes out to be a negative value. So you can state here as time increases, x is decreasing. So we can state it is the graph of a particle moving toward origin at constant velocity. Again, we are taking velocity to be constant because at every point of time in this straight line, the slope with the time axis is a constant. So these are the three motions you should always keep in mind, because in various questions we need to combine such type of graphs. Let us see some more displacement time graphs. If we analyze one by one these graphs, then in graph number 4 we can see, if we talk about a displacement time graph, there is a graph in which we can see particle starts from origin at t equal to 0 with a particular slope or velocity. But you can see when the particle moves, if we draw the tangents to the particle at various times, say we draw it at time t1 and then we draw it at after some time say t2, then you can see the angle which the tangent makes with the horizontal is decreasing. That means in this situation, when we talk about velocity of particle, it is tan theta. You can see here theta is decreasing, it is coming down. If velocity is decreasing, we can say the particle is retarding. So in this situation, at every point you can see this velocity is positive, but it is decreasing. So here acceleration we can call it to be negative, because when acceleration direction is opposite to the direction of velocity, then only the magnitude of velocity decreases. So this is the case where we can say a particle is moving with the positive velocity and negative acceleration. That means acceleration is negative opposite to the velocity. That means the magnitude of velocity decreases. It is a retarded motion. Similarly, when we talk about this graph number 5, you can again draw the tangents at time t1 and t2. In the beginning at t1 and after some time at t2. You can see we draw the tangents after some time at the higher time, the angle which the tangent is making with the positive direction of time axis is increasing. So here again we can state that velocity is equals to tan theta, which is positive but it is increasing. So if velocity is positive and increasing, that means acceleration vector is also positive, because when acceleration is in the direction of velocity, then only it increases. So it is a motion which we can consider as a particle is moving with the positive velocity and positive acceleration. That means it is a situation of an accelerated motion. Now we talk about this curve number 6. Here again you can see at two different times t1 and t2. If we draw the tangents, you can see at time t2 the tangent is steeper than the tangent at time t1. That means here, as it is making an angle, obtuse angle, it is making an obtuse angle, the velocity will be negative. So your velocity we can write again tan theta, which is negative, but as the steepness is increasing, this is also increasing. If velocity is negative and it is increasing, that means acceleration is also negative. So we can say particle, this is the curve for a particle moving with negative velocity and negative acceleration. And if velocity and acceleration are of same sign, this is the case of an accelerated motion. Similarly, if we talk about this curve 7, you can see that the steepness of tangent is decreasing from time t1 to t2. And as again the tangent makes an obtuse angle, the velocity, which is tan theta, is negative, but it is decreasing. So if velocity vector is negative and it is decreasing, that means acceleration vector will be in the direction opposite to that of velocity. It must be positive. Like in this case, again we can see the velocity is negative, the vector is negative, but it is increasing. So acceleration we have taken in the same direction of velocity, it is negative. But here, as velocity is negative and it is decreasing, the acceleration must be opposite. So this is the case which belongs to a particle moving with the negative velocity and positive acceleration, which is the case of a retarded motion. So always remember these graphs and the way how we are analyzing that which graph is corresponding to accelerated motion and which graph is corresponding to retarded motion. So all these graphs we are required to combine in case of a motion in which particle is accelerated as well as it is retarded. We'll also see some examples based on this. In this example, we are given with a tower over which a boy is standing who throws a ball up with a speed u. It goes up and finally it falls on the ground. And you can see it says a boy on the top of a tower of height h throws a ball up with the initial speed u. Now taking upward direction positive, we are required to draw the displacement versus time curve for ball's motion till it hits the ground. We can say if the starting point where the ball was thrown at t equal to 0 is taken as origin, and upward direction we consider as positive x direction and downward we take as negative x. So we can say it first move in positive direction. At some point of time its velocity becomes 0 and then it falls back, and final displacement will become x equals to minus h. So we draw the motion. We can take initial velocity as positive. Throughout the motion its acceleration is downward g, then acceleration we can take as minus g or minus 10 meters per second square. If we draw the graph for this motion, and if we draw the displacement time graph, it starts from x equals to 0 at t equal to 0. Say at a time t1 it reaches a maximum height. Say maximum height is h1. So we can say this is a height h1 where it reaches at a time t1. So this is the motion where velocity is positive and acceleration is negative. The graph will look like this. This is the graph for positive velocity and negative acceleration where it reaches the maximum height. And as we already studied, it will take the same time in coming back to the starting point. So at time 2t1 it will reach again back to the origin. So at time 2t1 it will come back to the origin like this. Here again x becomes 0. And say at a time t2 it will finally hit the ground. So we can state this graph will be further progressed, and at a particular position the time will be t2, and at this position the displacement will be equals to x will be equals to minus h. So this will be the complete curve. This is just the extension of this downward curve by which the particle will reach the ground. So this is the complete displacement time graph for the motion starting from the hand of the boy, reaching maximum height and finally hitting back to the ground. In this example, we are given with a car which moves at a velocity v0. If at t equal to 0 time, driver sees a need to apply the brakes and applies the brakes at a reaction time tr and finally comes to rest in a distance s after brakes are applied. We are required to draw the position time curve for car's motion. Now in solution, first we'll draw the realistic situation. So if this is the car and at t equal to 0, car was moving with a velocity v0 and the driver sees that he needs to apply the brake. So in this situation, up to the reaction time, the car will travel at a uniform speed v0. So car will travel a distance that is equals to v0 into tr. And at this position or at this time after tr, the brakes are applied, so car will be retarded and its velocity starts decreasing. And after some time, its final velocity becomes 0. It is given that when the brakes are applied, the car travels a distance s. This is the retarded motion. Or you can simply state this is the motion when velocity of car is positive but acceleration is negative. And in first part of journey, it moves with a uniform velocity. And now if we draw the velocity time or displacement time graph for this motion, we can simply state first part of motion will be a uniform motion. So displacement time graph for first part of motion, that is from t equals to 0 to t equal to tr, it will be a straight line like this. Straight line with a positive slope, and here tan theta can be written as v0. This is up to time tr. And from this time, the car starts retarding. If it starts retarding, the acceleration becomes negative and finally it is coming to rest at a time, say t final. So we can write at this t final, what is happening? The slope of this curve should become 0. And the final position where it becomes 0, this position will be the distance, which is v0 tr plus s. Up to this time tr, it will be covering a distance v0 into tr. Finally, it has traveled v0 tr, the displacement or distance covered in the reaction time, and further it has covered a distance s. So this is the distance s which the car has traveled in retarded motion. So this is the final displacement time graph. First part of which is a straight line which represents uniform motion. Second part is a curve which shows velocity is positive but acceleration is negative. So this is the retarded motion of the journey. This is the curve which is required to be drawn in the question. Let's analyze some different kinds of velocity time graphs. As we already studied that in velocity time graphs, the slope of velocity time graph gives us instantaneous acceleration, and the area between this curve and time axis gives us displacement. So here first we analyze three different kinds of VT graphs. The first one is the graph where velocity time graph is a horizontal straight line. So you can simply state the slope of the straight line is 0. So this is the graph which corresponds to 0 acceleration, or this we can consider the graph of uniform motion. Here particle moves with a constant velocity, that is uniform motion. If we talk about the second curve where velocity time graph is a straight line, and we can see this line makes an acute angle with the time axis. So here we can consider as in the straight line, at every point the angle with the time axis is constant. Here acceleration is a constant, and we can also call it positive because it makes an acute angle. That means the speed is increasing. So this is the case of increasing speed, where speed increases with time. In the third case, again it is a straight line. So here find the angle which the line makes with the time axis, it is obtuse. So here we can again state that acceleration is constant because in a straight line always the slope remains constant, the acceleration is negative, but here speed you can say it is decreasing. So this decreasing speed graph. So we can also state as the velocity is increasing, here velocity is positive, so acceleration is positive, as well as velocity is positive. That means the speed is increasing. Similarly, in this case, you can see acceleration is negative, but here velocity is positive. As acceleration is in the direction opposite to velocity, that means it must be decreasing. Here acceleration is in the direction of velocity, so that means the speed is increasing. Let's see some more velocity time graphs and their analysis. Say in graph number 4, if we can see that velocity time graph is a curve. That means here the angle which the tangent makes with the time axis is continuously changing. If we just think about the angle made by the tangent at two different times, say t1 and t2, you can see at time t2 the angle is increased. This theta is more than this theta. That means here we can say this is the situation of a variable acceleration, and as acceleration is given by the slope, here angle theta is increasing, so here we can simply state it is the case of increasing acceleration. And as theta is acute, here acceleration is positive, and as velocity is obviously positive in this case, so we can simply state both are in same direction, v vector and a vector. So here this is the case of increasing speed. Speed will continuously increase in this situation. If we talk about graph number 5, here we can again state as vt curve is a curve, this is the situation of variable acceleration. If we just talk about the slopes at time t1 and t2, you can see at time t1 and at time t2, we can see that at time t2 the straight line which is representing the tangent is steeper than the tangent at time t1. So we can state the acceleration is increasing, but here the angle made by the tangent with the time axis is obtuse, so here acceleration is negative. If acceleration is negative and as velocity in this situation is positive, we can state that the speed is decreasing. This is the situation of again increasing acceleration but decreasing speed. Again we must state as steepness of tangent is increasing, which is representing the acceleration, so it is increasing, but acceleration is negative because it makes an obtuse angle with the positive direction of time axis, so it is opposite to velocity. That's why we can say speed is decreasing. Similarly, in the third case or graph number 6, we can say again it is a curve. There's also the case of variable acceleration, and in this situation if at two different times t1 and t2, if we draw the slope, so at these two times we can see that the angle made by the tangent with the positive direction of time axis is acute. This is the case where we can say acceleration is positive, here velocity is also positive. So in this situation we can state speed is increasing because both are in same direction, but we can see that the slope steepness is decreasing or the angle made by the tangent with the time axis is decreasing. This is the case which belongs to the category of decreasing acceleration, but as acceleration is in the same direction of velocity, here speed will increase, so this is the case of increasing speed. I hope all of you have understood very well how to analyze such graphs. There can be more graphs we can draw on velocity time, but I leave it to you. You just draw, experiment on various ways, what all type of graphs can be drawn, and you just analyze in the same way. These are the basic analysis which we generally do for velocity time graphs. In this question, we are given with a tower from the top of which a ball is thrown upward with the initial speed u. It goes up and then finally hits the ground. Similar situation we have analyzed in a previous section when we were drawing displacement time graphs. Here in this question, we are said that a boy on the top of a tower of height h throws a ball up with initial speed u. And now taking upward direction positive, we are required to draw the velocity time curve. In the previous section, we have studied similar example where we have drawn a displacement time curve. Here we are required to draw the velocity time curve for ball's motion till it hits the ground. So say again we consider at t equals to 0, the ball was thrown. At time t1, it reaches maximum height where final velocity becomes 0. At time 2t1, it will be back to the same level from which it was thrown. And say at time t2, it will finally hit the ground in opposite direction with a velocity say vf. So in this situation, again, from the starting point, if we take it as origin upward direction, we consider as plus x-axis, downward we take as minus x-axis, and again the acceleration as throughout motion acceleration is in downward direction, this we take as minus g. Now in this situation, if we draw the velocity time curve for ball's motion, initially in the beginning you can say the particle was started with the positive velocity in upward direction. So initially at t equal to 0, the velocity was u, and at time t1 the velocity will become 0. So at time t1 the graph will come down like this, and it must be a straight line because the particle is moving at a uniform acceleration which is negative, so it is a straight line with a negative slope. And throughout motion we can see acceleration is constant, it is not changing, so the same straight line will be further extended, and say up to a time 2t1, one particle will reach the same level from where it was thrown. It will be having the same velocity u in downward direction at this point, this minus u, and it will further carry on till time t2, when particle will hit the ground where its velocity will be minus vf. This is the time t2 where particle will hit the ground. So same straight line will be carried on as velocity time graph, as throughout motion the acceleration is minus g. So as neither direction or magnitude of acceleration is changing, so the straight line will be carried on from a starting to the end point of motion, that is the time when this ball will hit the ground. In this example, it is said that a ball is dropped at t equal to 0 from a height h as shown. This ball is dropped at t equals to 0. As it is dropped, we can take its initial velocity to be 0. It collides elastically with the floor. Elastically collision or elastic collision means the ball rebounds with the same speed. Say it strikes the floor with the speed v, then it rebounds with the same speed v. You just always keep in mind one thing. When we talk about elastic collision, here no energy is lost. Always keep this thing in mind. The kinetic energy with which a ball strikes the floor, with the same kinetic energy it rebounds. That means the speed remains same, the direction of velocity only changes. And it rebounds to the same height. Obviously, if the velocity is same, it will be able to reach the same height where final velocity will again become 0. We are required to draw the velocity versus time graph for ball's motion, taking downward direction positive. In this equation, we are given that if we consider origin at the starting point, here we take downward direction as positive x and upward direction as negative x. Here, if we draw the velocity time graph for this motion, we can see at t equal to 0 particle started from rest, so graph must start from origin. And as throughout motion its acceleration is downward, so we take acceleration as plus g, because downward direction we are taking positive. So it will move with a uniform acceleration, so velocity time curve will be a straight line of positive slope. It will go on say up to a time t1, say at t equal to 0 it was released, then at time t1 we consider collision takes place. If ball will not lose any time in the contact, it will be rebounded, so it will take again the same time t1 in coming back. So the time at which it will reach the topmost point is 2t1. But at the instant of collision, the direction of velocity is reversed. So at this point, the velocity is say v. Say we take this velocity as v1. So it will also rebound with the velocity v1, but its direction is changed. So at this time t1, just after t1, the velocity is changed to minus v1, and then the same straight line will carry on till time 2t1. The initial time was 0, and at time t1, it strikes the floor, its velocity is reversed, and the straight line will remain same, because still during upward motion acceleration is positive, velocity is negative, and it is uniform. The same straight line will carry on in the graph with the positive slope, and its tan theta we can simply write it is equals to g, that is the acceleration. So this is the complete velocity time graph of the motion. For the same motion, it is not asked in the question, but if we wish, we can easily draw the displacement time graph also. Let us draw it. However, it is not asked in the question, but we can draw it. If we draw the displacement time graph, we can take up downward direction positive. So during downward motion, we can see velocity is positive as well as acceleration is positive. So we'll draw the graph like this, which corresponds to positive velocity and positive acceleration. And at time t1, it will strike the ground, which is at a position h. And then it will rebound when velocity becomes negative and acceleration is positive. So curve will be drawn like this. And at time 2t1, again the ball will reach the origin. So this is the graph for negative velocity and positive acceleration. So in such a way, you just need to combine various graphs which we already studied in earlier sections. Now let's discuss the acceleration time graphs. Just like to the case of displacement time and velocity time graphs, we can also plot acceleration time graphs if we are having the function of acceleration as a function of time. Now this graph is not of much importance in analysis of motion. Like if we just find out the slope or tangent at a point, the slope of this graph will be given by dA by dt. Here if we find out the value of dA by dt, you can simply state it as rate of change of acceleration. This rate of change of acceleration is not of much importance in analysis of rectilinear motion. However, if we find out the area below the graph up to time axis, this is given by integration of a dt from t1 to t2. This area will give us the total change in velocity between the time instants t1 and t2. Here this area can be simply written as change in velocity. In some of the questions, this area will be quite important to calculate, because it will directly give us the change in velocity from initial to final point. So at point A, the particle has a velocity va, and at point B, velocity would be vb. Then in this situation, we can simply write this area will give us vb minus va. If we just take up a simple example to analyze this concept, we can say if a particle starts at 5 meters per second and its acceleration varies according to the graph shown, we just draw the graph also. Find the velocity of particle at t equals to 10 seconds. The graph given to us is this. This is the acceleration time graph. which is a straight line. This is the acceleration time graph, which is a straight line inclined at an angle 30° with the time axis, and this starts with an acceleration of 2 meter per second square, and acceleration varies linearly with time. Here at t equals to 10 second, if we just have a look, say, and the particle has an acceleration given by a point C. This bottom is A and the starting point is B and this origin. So we can simply state at t equals to 10 second, the total change in velocity can be written as the area of this trapezium. So now in this situation, say this height from B to C is h, or it is an increase in acceleration. We can simply write here in this triangle, tan 30° will be equals to h divided by 10. So this will give us h is equals to 10 by root 3. Now in this situation, we can write in the solution that velocity of particle at 10 second is equals to velocity at time 0, which we already have, which is 5 meters per second, plus area OACB. This OACB area will be the net change in velocity which we add in the velocity at point B. This will give us the net velocity at point C or at time 10 second. Here if we find out the area OACB, then this area can be simply written as area of this rectangle plus area of this triangle. So area of this rectangle can be directly given as 10 multiplied by 2, that is 20, plus area of this triangle can be written as half into 10 by root 3. So this can be written as 20 plus 50 by root 3. So if this area, when we add here, this will be velocity at 10 second, we can directly calculate by 5, which is velocity at time t equal to 0, which is given the initial velocity, plus 20 plus 50 by root 3. So this will give us 25 plus 50 by root 3 meters per second is the answer to this question. So you can say in such questions, whenever we are given with the acceleration time graphs, we can find out the area of acceleration time graphs, and using this area we can find out the change in velocity. Like here what we have done in the initial velocity, we have added the area which will give us the final velocity of particle at t equal to 10 seconds.